Picture the Earth from far above, a blue and white marble turning slowly in the dark, its continents arranged like puzzle pieces drifting on a sea of stone. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From this great height, the world looks still. The brown shapes of the land seem fixed in place, the oceans wide and unmoving, the polar ice caps gleaming white at the top and bottom of the globe. Yet none of it is still. Every continent you can see is moving, very slowly, in a direction it has been traveling for millions of years. The motion is so gentle that you could never feel it. Each year, the great plates of the Earth's outer shell shift by only a few centimeters. That is about the same speed as your fingernails grow. Stand in one place for a lifetime, and the ground beneath you will have crept a meter or two in some quiet direction. Stand there for 1,000,000 years, and you would have moved the length of a long river. Stand there for 100 million years, and the ocean itself would have opened or closed beside you. This is the strange, slow truth that geologists have come to accept. The skin of the Earth is broken into enormous slabs of rock called tectonic plates. There are 7 large ones and many smaller ones, fitting together like the cracked shell of a hard-boiled egg. They carry the continents on their backs, and they carry the seafloors too. Beneath them lies a layer of hot, soft rock that flows over long stretches of time, the way thick honey might creep across a cold plate. The plates float on that flowing layer, and they move. What still puzzles many geologists is the deeper question of why. We know the plates move. We can measure their motion now with satellites, watching North America drift away from Europe at about the rate that a fingernail grows. We know the rough shape of the engine that drives them, somewhere down in the mantle, that thick layer of hot rock between the thin crust and the molten core. But the exact mix of forces that pushes and pulls each plate remains an open question. Some researchers think the plates are mostly dragged by their own cold, heavy edges sinking into the deep. Others think they are mostly carried along by slow currents of hot rock churning below. The truth is probably some blend of both, and that blend is still debated. If you could speed up time and watch the Earth from above for hundreds of millions of years, the view would no longer look still. The continents would slide, collide, split apart, and rearrange themselves into shapes that no living human has ever seen. Long ago, all of them gathered into a single great landmass, a supercontinent we now call Pangaea. Before Pangaea, there were others. And after Pangaea broke apart into the continents we know, the pieces did not stop moving. They are still drifting, even tonight, while you lie quietly listening. The scale of this is hard to hold in the mind. The Atlantic Ocean, which seems so vast and ancient, is actually a young ocean. It did not exist when dinosaurs first appeared. The Himalayas, which look like the most permanent thing in the world, are young mountains, still being pushed upward by the slow crash of India into the rest of Asia. The dry red rocks of the American West once sat near the equator, in warm, shallow seas. The coal beneath England was once a steaming swamp near a different ocean entirely. Every patch of ground on Earth has a long, quiet travel story behind it. For tonight, picture that blue marble turning gently in the dark. Imagine the continents not as fixed shapes on a map, but as great, slow ships, drifting on currents of stone too deep and too slow to see. Imagine that the place where you are lying right now, the room around you, the floor beneath the building, the rock beneath the floor is moving. Not in any way you can feel, not in any way that should worry you, just moving, the way clouds move when you are not looking at them, the way a shadow lengthens across a wall in the late afternoon. The Earth has been doing this for billions of years. It will keep doing it long after this night is over. And the question of exactly how and exactly why is one we will sit with together over the hours ahead. More than 100 years ago, a quiet German scientist looked at a map of the world and noticed something strange. His name was Alfred Wegener. He was not a geologist by training. He studied weather and air, the cold winds of the polar regions, the way storms moved across the sky. But on that ordinary day, with an ordinary map spread before him, he saw what so many others had seen and dismissed. The coast of South America curved inward in just the right way to fit against the coast of Africa, like two pieces of a torn page, separated by a wide blue ocean. He was not the first to notice. Others had pointed at the same shapes for centuries, but Wegener took the idea further than anyone before him. He wondered if the continents had once been joined. He wondered if they had drifted apart slowly over unimaginable spans of time. In 1912, he stood before a small audience of scientists and shared this thought. He called the ancient single landmass Pangaea, a word built from Old Greek roots meaning all the lands, and the world of science, for the most part, laughed. To understand why they laughed, picture the scale of what he was proposing. The continents are huge. Africa alone covers more than 30 million square kilometers. That is roughly 3 times the size of the entire United States. North America is a slab of rock and soil stretching almost 5,000 kilometers from coast to coast. Each continent is not a thin sheet, but a thick wedge of stone reaching tens of kilometers down into the earth. The deepest roots of the oldest mountains push down farther than commercial airplanes fly above us, and Wegener was suggesting that these monstrous slabs, weighing trillions upon trillions of tons, slid sideways through solid rock. Not over days, not over centuries, over hundreds of millions of years. The speed he imagined was about the rate at which your fingernails grow, a few centimeters each year. Slow enough that a person could stand on the moving ground for an entire lifetime and never feel a thing. To the geologists of his time, this seemed absurd. They could not picture what force could possibly push a continent. The Earth, they believed, was a fixed and solid thing. Mountains rose, oceans formed, but the great landmasses stayed where they had always been. Wegener's idea had no engine, no mechanism. He could describe the puzzle pieces, but he could not say what hand had moved them. Yet the evidence kept whispering. He gathered it carefully. The same fossil ferns appeared in coal beds on continents now separated by thousands of kilometers of open sea. The bones of small ancient reptiles, animals that could not possibly have swum across an ocean, lay buried on both sides of the Atlantic. Glacial scratches on stones in Africa and India pointed in directions that only made sense if those lands had once sat near each other, near a frozen South Pole that no longer reached them. Wegener wrote a book in 1915, refining his case year after year, edition after edition. The response from most established scientists was cold. Some called his ideas a fairy tale. One famous geologist said the theory was delirious ravings. Wegener kept working. He returned again and again to Greenland to study its ice and weather, the very kind of fieldwork he loved most. On one of those expeditions in 1930, he died in the snow. He never lived to see his idea accepted. For decades after his death, the theory of drifting continents sat in the back rooms of science. A curiosity, a footnote, something taught with a wink, as an example of how clever people can sometimes go astray. The mainstream view held that the continents were fixed in place. And then slowly, the evidence began to pile up in ways that could no longer be ignored. New tools mapped the floor of the ocean. New instruments measured the magnetism of ancient rocks. New voices began to ask the same question Wegener had asked. By the late 1960s, the idea he had been mocked for had become the foundation of modern Earth science. The puzzle pieces fit. The continents moved. Pangaea had been real, but here is the gentle mystery that remains. Even now, more than a century after that first quiet observation, scientists still argue about exactly how the continents move. They agree that they do. They agree on much of the choreography. Yet the deeper question, the one Wegener could not answer, still lingers in the background of every geology textbook. What truly pushes these vast slabs of stone? We will sit with that question many more times tonight and let it carry us gently onward. Before there was a Pangaea, there were older lands that came together and broke apart in slow, patient cycles. The story of how the great supercontinent took shape begins long before its famous name. It begins with smaller continents drifting across a younger Earth, gathering and parting like ships in a slow harbor. Geologists believe that several of these gatherings happened in deep time. Pangaea was simply the most recent, and the one whose memory the rocks still hold most clearly. The pieces that would become Pangaea began drawing together roughly 335 million years ago. This was the late part of a long age called the Carboniferous, a time when vast coal forests covered much of the warm, wet land. The continents we know today did not yet exist as separate shapes. Instead, two enormous landmasses moved slowly toward each other across the planet. One was called Laurussia, sometimes also called Euramerica, made of what would later become North America and most of Europe. The other was Gondwana, a southern giant that held the future South America, Africa, India, Antarctica, and Australia. Picture these two great lands sliding across the planet at the pace a fingernail grows. That is the speed of continents then and now. The ocean between them, an old sea called the Rake Ocean, narrowed year by year. Its floor was pulled downward into the deep earth as the lands above pressed closer. For tens of millions of years, this slow closing went on, quiet and unstoppable, while strange amphibians crawled through the swamps and dragonflies the size of small birds drifted through warm air. When Laurussia and Gondwana finally met, they did not meet gently. The collision raised long mountain ranges along the seam where they joined. In what is now the eastern United States, this collision built the Appalachian Mountains. In Europe and North Africa, the same crash raised the Variscan and Mauritanic ranges, whose worn-down roots can still be traced today. These were once towering peaks, perhaps as high as the modern Himalaya. Time and rain have softened them into the gentle, rounded hills we see now, but the rocks remember. The full assembly of Pangaea was not a single event. It happened in stages over more than 100 million years. Smaller landmasses, called terranes, kept arriving and welding themselves onto the growing supercontinent. Siberia drifted in from one side. The blocks that would become parts of China remained partly separate, drifting nearby but never fully joining the main mass. So even at its largest, Pangaea was not quite the whole world. A few stray pieces of land floated in the surrounding ocean, like islands waiting at the edge of a great gathering. By about 300 million years ago, Pangaea had taken its rough, famous shape. Seen from above, it looked something like a vast crescent or a wide letter C, curving around a deep bay of warm ocean. That bay is called the Tethys Sea, and it opened toward the east. The shape of Pangaea was not a perfect oval, as older textbooks sometimes showed. The true outline, as best as researchers can reconstruct it, was uneven, with long peninsulas and inland seas reaching deep into the interior. Here the mystery begins to deepen. How exactly the pieces fit together remains a question with several answers. Most reconstructions agree on the broad picture, but the details, especially along the edges, are still debated. One model is called Pangaea A, the classic arrangement first sketched by early researchers. Another, called Pangaea B, places North America farther south, pressed closer to South America. Some researchers favor one, some favor the other. The rocks give hints in both directions, and the question stays open. What conditions made this gathering possible at all? That is another quiet puzzle. The slow churn of hot rock deep below the surface seems to have pulled the continents inward during this stretch of time. Why the currents flowed that way then, and flow differently now, is something geologists are still working to understand. Some think the arrangement of older ocean floors guided the motion. Others think the pattern arose from changes far deeper, near the boundary between the mantle and the core. What we can say is this. For a brief moment in the long life of Earth, almost all the dry land gathered into a single shape, surrounded by a single great ocean. The shape held for perhaps 50 million years before it began, very slowly, to come apart again. The reasons it formed and the reasons it broke are pieces of the same long mystery. We see the outline of what happened. We are still learning the why. Around the supercontinent of Pangaea stretched a single, enormous ocean. Geologists call it Panthalassa, which means simply the all-sea. It wrapped around the world in one vast, unbroken sheet of water. To imagine it is to picture a globe of mostly blue, with one great clump of land floating in the middle. The waves of Panthalassa rolled across distances that no modern ocean can match. This ocean was made of the same simple thing our oceans are made of today. Water, just hydrogen and oxygen, bound together in tiny molecules, repeated countless times. Yet the story of how that water arrived on Earth is one of the quietest mysteries in all of geology. We are not entirely sure where it came from. One idea is that the water was here all along. As Earth gathered itself together from a cloud of dust and rock, tiny grains carried trace amounts of water locked inside them. Heat and pressure squeezed that water out over millions of years. volcanoes spat it into the sky as steam. The steam cooled, fell as rain, and slowly filled the low places of the young planet. Another idea is that much of the water arrived later, from far beyond Earth itself. Some researchers wonder if comets, those icy travelers from the cold edges of the solar system, brought water in their slow falls toward the inner planets. Others point to a kind of ancient asteroid, rich in water-bearing minerals, that may have rained down during Earth's early years. The truth may be a mixture of all of these things. The question remains open. What we do know is that the water in Panthalassa carried dissolved salts, just as our oceans do today. Sodium, chlorine, magnesium, calcium, potassium. These elements were pulled from the crumbling stone of the continents by rain and rivers. Year after year, century after century, the rivers carried tiny grains of mineral down to the sea. The sea grew salty in slow, patient layers. The same salts still drift in seawater now, the inheritance of a planet weathering itself. Beneath the waves of that great ocean lay a floor of dark rock, mostly basalt. Basalt is what cools and hardens when lava from deep inside the earth meets cold seawater. It is heavy, dense, and rich in iron and magnesium. Run your hand across a piece of seafloor basalt today, and you are touching something that was once a glowing red liquid, born from a place miles beneath the surface. The iron in that basalt, and the iron in your own blood, and the iron at the very center of the earth, all share a strange and distant origin. None of it was made on this planet. Iron is forged inside stars, in the slow furnaces of their cores, and scattered across space when the largest of those stars die. Every iron atom in Pangaea's mountains, in Panthalassa's seafloor, in the spinning core that gives our world its magnetic field, was once part of a star that no longer exists. The Earth is, in a sense, a quiet gathering of stardust that learned how to hold an ocean. The air above Panthalassa was different from the air we breathe now. It held more carbon dioxide. The world was warmer in places, drier in others. Oxygen was there, made by countless tiny plants and ocean microbes, but the balance of gases shifted slowly across deep time. The clouds above that single sea would have looked familiar, though. White, soft, drifting. Rain still fell. Storms still moved across the water in long, curving arcs. Down in the depths, the chemistry of the ocean did its slow work. Calcium and carbon and oxygen joined together to form the shells of countless small creatures. When those creatures died, their shells settled in soft drifts on the seafloor. Over millions of years, those drifts pressed themselves into limestone. Some of the limestone we walk on today, in quiet hillsides far from any sea, was once the bottom of Panthalassa. Everything in that ancient world was made of pieces borrowed from somewhere else. Hydrogen from the earliest moments after the universe began. Oxygen and carbon and calcium from the hearts of long-dead stars. Iron from supernovas. Water perhaps from comets, perhaps from the dust of the forming Earth itself, perhaps from both. The single ocean that surrounded Pangaea was a gathering place for all of these wanderers. When we look at the sea today, we are looking at the same materials, only rearranged. The molecules have traveled through ancient reefs, through dinosaurs, through glaciers, through clouds. They have rested on the floor of Panthalassa, and they rest beside us now, in every glass of water, in every doctor. To understand why the continents move at all, we have to picture what lies beneath them. The ground under our feet feels solid and still. The rock seems permanent, but the crust we walk on is only a thin skin. It floats on something much deeper, much hotter, and much older than anything we can see. Below the crust sits the mantle. The mantle is a thick layer of hot rock that reaches down nearly 3,000 kilometers toward the center of the planet. It is not liquid in the way the ocean is liquid. It is solid rock that flows. Imagine warm taffy or thick honey left in the sun. Over thousands of years, this rock bends and creeps and slowly turns over itself. That slow turning is the engine that moves the world. Heat drives the engine. Some of that heat is left over from the birth of the Earth, when dust and stone crashed together and warmed the young planet. Most of the heat, though, comes from something quieter. Deep inside the rock, tiny amounts of natural radioactive material slowly break down. Each break releases a small puff of warmth. Multiplied across the whole planet and across billions of years, those small puffs add up to a steady, gentle furnace. This warm interior creates a slow churning called convection. Hot rock near the core rises because heat makes it slightly less dense. Cooler rock near the surface sinks because it is slightly heavier. The rising and the sinking form huge, lazy loops inside the mantle. Each loop may take 100 million years to complete a single turn. The plates of the crust ride along on the top of these loops, like leaves drifting on the surface of a slow river. That, at least, is the picture most geologists carry in their minds. But the picture is not complete. Researchers still wonder which force matters most. Some think the rising and sinking of the mantle itself drags the plates along from below. Others think the real pull comes from the edges of the plates. When a slab of cold crust sinks into the mantle at a trench, its own weight tugs the rest of the plate behind it, like a heavy tablecloth slipping off a table. This idea is called slab pull. A third idea, called ridge push, suggests that fresh hot rock rising at the seams between plates gently shoves them apart. The honest answer is that all three forces probably work together. How much each one contributes is still an open question. Some plates seem to be pulled strongly by sinking slabs. Others seem to drift along without much tugging at all. The deeper the geologists look, the more they find that the engine has many moving parts, and not all of them are well understood. Gravity quietly shapes everything. It pulls the heavy, cold plates downward. It holds the mantle in place against the spin of the Earth. It even helps decide which rocks float higher and which sink lower. Lighter granite rises into continents. Denser basalt sits beneath the oceans. Without gravity, none of this layering would settle into the patterns we see. Pressure plays its part too. The deeper you go, the more crushing the squeeze becomes. Rocks that would melt at the surface stay solid down there because pressure holds their atoms tightly together. Yet when a plate breaks or bends in just the right way, the pressure can drop, and the rock can suddenly soften and flow. This is one reason volcanoes appear where they do. The Earth releases its heat in pulses, in cracks, in slow links. The magnetic field also weaves through the story, though its role is more subtle. It is generated by churning iron in the outer core, far below the mantle. The field does not push the plates, but it leaves a record. As fresh rock cools at the seams between plates, it locks in the direction of the magnetic field at that moment. Reading those frozen signals helped us understand that the seafloor itself was spreading. We will return to that strange discovery later. For now, it is enough to picture the engine. A vast, slow boil of stone. A planet warmed from within by ancient leftover heat and the soft drip of radioactive decay. Currents that take 100 million years to complete a single turn. Plates dragged, pushed, and pulled by forces that overlap and argue with one another. And somewhere in all of it, the question of what truly drives the dance still waits for a clearer answer. The world beneath us is not still. It is breathing, very slowly, in a rhythm older than every mountain, every ocean, every story ever told above it. Somewhere beneath the dark Atlantic, right now, the seafloor is splitting open. It happens slowly, far below the reach of any sunlight, along a long curving seam that runs almost the full length of the ocean. This seam is called a mid-ocean ridge. It is the longest mountain chain on Earth, and almost no one has ever seen it. To picture the scale, try this. The ridge system that wraps around our planet runs for about 40,000 miles. That is long enough to circle the equator 1.5 times. If you could lift the entire chain out of the water and lay it across the land, it would stretch from city to city, across continents, across deserts, across forests, and still keep going. Yet most of it sits hidden under 2 miles of cold seawater, in a darkness so complete that the only light comes from rare glowing creatures and the occasional red shimmer of hot vents. Along this seam, the two sides pull apart at about the speed your fingernails grow. Hold up your hand for a moment in the quiet dark. Look at the soft, pale crescent at the base of a nail. That tiny rate of growth, slow and patient, is roughly how fast the Atlantic is widening tonight, about 1 inch a year, maybe 2 in some places. It's almost nothing on a human scale, but give that movement 100 million years and an entire ocean opens between continents. The size of the gap is hard to feel. Think of standing on a beach in Portugal, looking west. Then think of someone standing on a beach in Newfoundland, looking east. The water between you is nearly 2,000 miles wide. Every inch of that water sits above seafloor that did not exist when the dinosaurs were young. The Atlantic is a fresh ocean, geologically speaking. It grew inch by inch from a single crack. The heat at these spreading edges is something the mind struggles to hold. Where the plates pull apart, molten rock rises from below to fill the gap. That rock comes up at temperatures near 2,000 degrees Fahrenheit. Pour boiling water from a kettle and feel the steam on your skin. That water is around 200 degrees. The rock pouring out at the ridge is 10 times hotter. Cold seawater hits it and quenches it in seconds, turning it into dark, glassy pillows that pile up along the seam. In a few rare places, this rift breaks the surface. Iceland is one of them. The island sits directly on top of the mid-Atlantic ridge, slowly tearing in half. You can stand in a quiet valley there and place one hand on rock that belongs to North America and the other on rock that belongs to Europe. The two continents are drifting away from each other right beneath your feet at the speed of a fingernail for as long as you stand there. The valley grows a little wider each year. Most visitors never notice. The change is far too slow for human senses to feel. Other rifts on land are still in their early stages. In East Africa, a long crack runs through the ground from the Red Sea down through Ethiopia, Kenya, and Tanzania. This is the East African Rift, and one theory holds that it is the slow birth of a future ocean. If the pulling continues, a strip of land could one day break free from the rest of Africa and drift east. Whether that future ocean truly forms and how long it might take remains an open question. Some researchers think the rift will stall before it splits all the way through. Others think it will keep going. The Earth, as always, does not tell us its plans. Hold one more comparison in your mind before you drift further. The deepest ridge valley is about 1.5 miles below sea level. Above it, 2 miles of cold, dark water press down. If you placed Mount Everest into that valley upside down, its peak would still not reach the surface of the sea. And along this hidden, sunken mountain chain, new crust is being made tonight, in absolute silence, in absolute darkness, by an Earth that has been doing this work for billions of years. How much of the ocean floor has been built this way is something geologists can map but still struggle to fully picture. The numbers are large, the time is long, the motion is gentle. And the question of how the engine beneath truly drives this slow opening, year after patient year, is one we will sit with again. For now, simply rest with the thought of a planet quietly, endlessly, pulling itself apart at the seams. Imagine for a moment that you could float high above the western edge of South America. Below you, the long spine of the Andes rises out of the green continent like a wrinkled ridge along the back of some sleeping animal. The peaks are sharp and white with snow. The valleys between them are deep and shadowed. To the west, the dark blue Pacific stretches out, calm at the surface, hiding a long, narrow trench just offshore. That trench is the seam. It is the line where two great plates meet, and one is slowly diving beneath the other. This is what a collision looks like on the surface of our world. It does not happen all at once. It happens over millions of years, slower than the growth of a fingernail, and yet the marks it leaves are written across whole continents. Where plates crash together, the earth wrinkles. It folds. It pushes upward. It builds mountains the way you might push the edge of a rug across a polished floor and watch the cloth bunch into ridges. Now drift north, across the equator, and look down at the Great Wall of the Himalayas. Here you see the most dramatic collision still happening on Earth. The plate carrying India is pressing into the plate carrying the rest of Asia. The land between them has nowhere to go but up. The peaks rise more than 5 miles into the thin, cold air. Their flanks are jagged and gray, streaked with blue ice and white snow. Glaciers wind down through the high valleys like slow frozen rivers. The mountains are still growing, a tiny bit every year, even as wind and water try to wear them down. It is strange to think that the rocks at the top of these peaks once lay at the bottom of an ancient sea. Geologists have found seashell fossils high in the Himalayas, lifted into the clouds by the long, slow push of one continent into another. Pangaea, the supercontinent we have been wondering about, broke apart in part because pieces of it began to drift toward new collisions. India was once a separate island continent, drifting north across a warm ocean for tens of millions of years before it slammed, gently and endlessly, into Asia. Not every collision builds mountains the same way. Where an ocean plate meets a continental plate, the heavier ocean plate slides under and dives deep into the earth. Above that diving edge, volcanoes often grow. The Andes are dotted with them. Their cones rise from the high plateau, some still smoking, some long quiet. The land there is brown and dry and dust-colored, with patches of salt flats that shimmer pale white under the high sun. The air is thin, the colors are stripped and clear. Where two ocean plates collide, the result is different. One slides beneath the other, and a chain of volcanic islands rises along the seam. The islands of Japan formed this way. So did the long curving arcs of the Aleutians, sweeping across the cold gray waters of the North Pacific. Seen from above, these island chains look like stitches in the skin of the sea, small green and brown shapes scattered along an invisible line. And where two continents collide, neither one wants to dive. They are both too thick, too light, too stubborn, so they crumble. They push against each other and fold their edges upward into broad, high plateaus. The Tibetan Plateau is the largest of these. It is a vast, cold land of brown grass and pale rock, lifted nearly 3 miles above the sea, stretching for thousands of miles in every direction. What remains a quiet, open question is how exactly these collisions begin. We can see them happening now. We can map the slow movement of the plates with great precision. But the earliest stages of a collision, the moment when one plate first commits to diving beneath another, are harder to read. Some researchers think the process may start at weak spots in the crust where old scars from earlier collisions never fully healed. Others wonder whether the cooling of an old ocean plate eventually makes it heavy enough to sink on its own. The evidence is incomplete. The deep beginnings are buried under the very mountains they helped to build. For now, picture the long spine of the Andes again, glowing faintly pink at sunset. Picture the Himalayas under a clear, cold sky, their peaks catching the last light. Picture the dark trench just off the coast of Japan and the small green islands rising from the sea. Each one is a place where the earth is still slowly, patiently pressing itself together. Each one is a question still being written far below. Not every meeting between two plates is loud. Some of them are quiet, some of them just slide. Where one plate moves past another, neither sinking down nor pushing up, the edges grind side by side in slow motion. This is the third great kind of plate boundary, and it may be the strangest of all. It builds no mountains. It opens no oceans. It simply slides year after year with a patience that is hard to imagine. Geologists call these places transform boundaries. The word transform sounds dramatic, but the movement is gentle most of the time. Two huge slabs of rock, each carrying continents or seafloor, press their edges together and shuffle past one another a few centimeters each year. That is about the speed a fingernail grows. You could stand on such a boundary and feel nothing at all. The ground beneath your feet would seem perfectly still. And yet deep below, the stone would be sliding. The most famous of these sliding edges runs through the western coast of North America. It is a long crack in the crust, hundreds of miles in length, where the Pacific Plate brushes past the North American Plate. From the air on a clear day, you can sometimes see it as a thin scar across the dry hills, a line where rivers bend and valleys form in odd straight rows. The land on one side is slowly drifting north. The land on the other side is staying put. Given enough time, many millions of years, places that are now far apart will become neighbors. But the sliding is not always smooth. That is where the mystery deepens. Most of the time, the two plates are locked. Friction holds them in place along the rough surfaces of broken stone. Pressure builds. Year by year, the deeper rock keeps trying to move, while the surface refuses to slip. Energy gathers in the rock like a held breath. Then, sometimes after centuries of silence, the edges release. The plates jump forward in a few seconds. We feel that release as an earthquake. What lies between the locked patches is one of the open questions of modern geology. Some sections of these faults seem to slide quietly all the time, in a slow creeping motion researchers call fault creep. Other sections stay frozen for hundreds or thousands of years. Why some parts creep and others lock is not fully understood. One idea points to the kind of minerals in the rock. Certain clays, soft and slippery when wet, may let the stone slide easily. Other ideas focus on the heat, the pressure, the fluids trapped in tiny cracks far below. The answer is likely a mix of all of these. The full picture remains incomplete. Deeper still, the fault does not stay a simple crack. As it descends into the crust, the stone grows hotter. Around 10 or 15 kilometers down, the rock no longer breaks cleanly. It bends. It flows very slowly, like extremely thick honey. Geologists believe that below this depth, the plates still slide past each other, but without sudden jumps. There are no earthquakes that deep along transform faults. There is only the slow, ductile pull of warm rock giving way. We cannot see this directly. We only know it through the patterns of small tremors and the way seismic waves move through the ground. Some transform boundaries do not run through continents at all. Most of them, in fact, lie far out under the oceans. They cut across the mid-ocean ridges in short, perpendicular jogs, creating a strange staircase pattern on the seafloor. From above, the ocean floor looks scarred by these offsets, as if a great hand had sliced and shifted long ribbons of stone. These oceanic transforms are harder to study, hidden under miles of dark water. Submarines have visited only a few. Much of what happens along them remains a guess based on faint signals reaching the surface. There is something humbling about these quiet edges. They do not announce themselves the way volcanoes do. They do not raise mountains for us to admire. They simply pass each other, century after century, mostly in silence, occasionally in a sudden lurch. Whole landscapes are slowly being rearranged by this sliding. Rivers are being bent, coastlines are being stretched. And the science of why these faults behave the way they do, when they will lock, when they will creep, when they will slip, is still being written. Researchers gather more data each year. The puzzles do not so much vanish as shift into new shapes. For now, somewhere far beneath the soft ground, two great plates are grinding past one another in the dark. They are doing it tonight. They will be doing it tomorrow. The question of exactly how and why drifts on. Mountains do not stand still, even though they look like the most patient things on Earth. They rise, they crumble, they rise again, all in slow rhythms that stretch across hundreds of millions of years. When two plates push against each other, the land between them has nowhere to go but up. Stone folds like soft cloth, layers buckle and stack. the crust thickens, and a new mountain range is born from the slow squeeze of a planet that never stops moving. The Himalaya is the clearest living example. About 50 million years ago, the slab of crust carrying India drifted north and met the larger plate carrying Asia. The two pieces of land could not pass through each other, so they crumpled. The seafloor that once lay between them was lifted into the sky. Even today, geologists find the shells of ancient sea creatures pressed into rock high on the slopes of Everest. Tiny spirals of stone, once resting in a warm, shallow sea, now sit in thin, cold air above the clouds. This is the rhythm the planet keeps. Plates drift, plates meet, mountains grow. Then wind and water begin their patient work, wearing the peaks back down grain by grain. Rain dissolves the stone. Rivers carry it to the sea. Glaciers grind valleys deep into the rock. Over time, a mountain that once towered above the clouds becomes a low ridge of weathered hills. Given long enough, it becomes a plain. The Appalachian Mountains of eastern North America tell this older story. They are quiet, rounded, soft with forest. But hundreds of millions of years ago, when Pangaea was still forming, the Appalachians may have stood as tall as the Himalaya does now. Time has worn them down. The bones of those ancient peaks still remain, buried under soil and trees, their roots reaching deep into the crust. What the eye sees today is only the lower stub of something that once scraped the sky. Mountains, then, are not permanent. They are moments in a long cycle. Rise, stand, erode, vanish. And while the surface peaks come and go, the deep roots can linger for a very long time. When geologists look at modern continents, they find old mountain roots tucked inside them, like the rings of a tree. These hidden seams show where ancient lands once collided, fused, and stayed joined long after the high peaks were gone. This rhythm is part of why Pangaea matters so much to the story. The making of a supercontinent is, in many ways, the making of many mountain ranges all at once. As pieces of crust came together to form Pangaea, ranges rose along every place they met. The Appalachians, the old Variscan belt running through Europe, the Ural Mountains between Europe and Asia, the long bones of mountains in northwest Africa. Each of these is a scar left by a collision. Each one marks a place where two pieces of the world became one. And here the open questions begin again. Geologists can map these old collision zones, but the exact timing of each one is still debated. Some ranges seem to have risen in pulses, with periods of fast growth followed by long quiet. Others appear to have grown more steadily. No one is sure why. One idea is that the deep flow of hot rock beneath the plates surges and slows in cycles of its own. Another possibility is that the speed of collision changes as the plates rearrange themselves on the planet's surface. The evidence is incomplete, and the rhythm beneath the rhythm remains hard to read. There is also the question of how high a mountain can grow before its own weight begins to limit it. The crust beneath a great range sinks downward, like a boat heavy with cargo. The deeper it sinks, the harder it is for the peaks above to climb higher. Some researchers suspect there is a kind of natural ceiling, set by the balance between uplift and gravity. Others wonder if past mountains, in warmer or thicker crusts, may have risen far above anything we see today. The fossils of those lost summits, if they ever existed, have long since washed into the sea. so the planet breathes through stone. Plates drift together and apart. Mountains rise where they meet, and rivers carry them quietly back down. Sediments settle on the seafloor, are pulled into the crust, and one day perhaps lifted again into new peaks. Nothing is lost. Nothing is final. The hills you see on the horizon are simply the present chapter of a story that was already old when the first continents formed, and that will keep turning long after the names we give to mountains have faded from any map. At the edges of certain oceans, the seafloor does something strange. It curves downward. It folds into a long, narrow valley that runs for thousands of miles. These valleys are called trenches, and they are the deepest places on Earth. In some of them, the water is so deep that the surface lies 7 miles above the bottom. If you dropped a tall mountain into one, the peak would still be hidden beneath the waves. A trench is not just a low spot. It is the doorway where one plate slides beneath another. The seafloor on one side is pushed down. It tilts, it bends, and then it sinks into the hot rock below slowly over millions of years. Geologists call this slow swallowing subduction. The plate disappears from the surface and melts back into the deep. This is one of the great quiet wonders of our planet. The ocean floor is not permanent. It is born at the long ridges in the middle of the sea, where fresh rock rises from below. It travels outward, drifting for tens of millions of years. And then at the trenches, it slips beneath another plate and vanishes. The Earth is constantly making new seafloor and unmaking the old. No piece of ocean crust lives forever. The deepest trench we know is in the western Pacific. It curves like a long scar across the seabed, more than 1,500 miles from end to end. Down at its lowest point, the pressure is more than 1,000 times what we feel on land. The water is cold and black. Strange, soft creatures live there, drifting along the muck. We have sent only a handful of vessels to the very bottom. Most of it remains unseen. What happens to a plate after it sinks is still partly a mystery. Some of it melts, some of it stays cold for a long time, sliding down through the hotter rock like a slow stone falling through honey. Using earthquake waves, geologists can sometimes trace these old slabs hundreds of miles below the surface. A few may even reach the bottom of the mantle, near the outer edge of the core. One idea is that these sunken slabs pile up down there, forming great cold graveyards of ancient seafloor. Another idea is that they break apart and mix back into the deep, slow currents of the mantle. Both pictures may be partly true. The full story is not yet clear. Trenches matter for Pangaea too. When that giant landmass began to break apart, the seafloor between the new pieces had to go somewhere. As the Atlantic grew, the old Pacific seafloor was steadily pulled down into trenches around its edges. This ring of swallowing zones is sometimes called the Ring of Fire because of the many volcanoes that rise above it. The volcanoes form when sinking plates release water into the hot rock above, lowering its melting point and creating molten pools that rise to the surface. In a strange way, every trench is connected to every ridge. The seafloor born at the ridge must, eventually, find a trench. If too much new crust is made, somewhere else the old crust must sink faster. The balance is not perfect, and it shifts over millions of years, but the system as a whole keeps moving. The surface of the Earth is in a quiet, endless trade. What we do not fully understand is why trenches form where they do. The starting of a new subduction zone is one of the deepest puzzles in geology. Plates are heavy and strong. Bending one downward takes enormous force, yet somehow, every so often in Earth's history, a fresh trench appears. One theory is that old, cold, dense seafloor eventually becomes heavy enough to begin sinking on its own. Another theory is that two plates collide in just the right way, and one is pushed under the other. A third idea is that some weakness in the crust, perhaps an old fracture from long ago, gives way. Researchers are still piecing it together. There are hints in the rock that subduction may not have always worked the way it does now. Early in Earth's history, the mantle was hotter, and the plates may have been softer and thinner. Whether trenches existed 3 or 4 billion years ago is still debated. Some geologists believe subduction began very early. Others think it only became common later, after the planet had cooled enough for strong, brittle plates to form. The clues are scattered in tiny crystals and old, deformed stones. So tonight, picture those long, dark trenches at the edges of the sea. Quiet, patient, slowly drawing the old floor of the world back into the deep. Long before anyone could measure the slow drift of the plates, before satellites could track the movement of continents down to the millimeter, the ground itself held a strange and quiet clue. The clue was buried in stone. It was written in the bones of creatures that had been dead for hundreds of millions of years. And when people finally read it, the message was almost too strange to believe. The same fossils kept turning up on opposite shores of the world. Picture a small reptile, no bigger than a house cat, with a long body and short legs and a tail that swept behind it as it walked through ancient swamps. Its name is Mesosaurus. It lived around 290 million years ago, paddling through shallow freshwater lagoons, eating tiny shrimp-like creatures. Its bones have been found in only 2 places on Earth. One is in southern Africa. The other is in eastern South America, nowhere else. Not in North America, not in Europe, not in Asia. Mesosaurus could not have crossed an ocean. Its bones say so. The shape of its body, the structure of its limbs, the salt-poor lagoons it lived in, everything tells us this was a freshwater animal that swam in calm water. The Atlantic Ocean, thousands of miles wide and salty as tears, would have been a wall it could never have passed. And yet its fossils sit on both shores, as if the 2 coasts were once a single place. There are others. A fern called Glossopteris grew across vast swaths of the southern world during the same long age. Its leaves were broad and tongue-shaped, with a soft network of veins running through them. Its seeds were heavy. They could not blow on the wind across an ocean. They could not float for weeks on salt water and still sprout. And yet the fossil leaves of Glossopteris have been found in South America, in Africa, in India, in Australia, and in Antarctica. 5 continents, all separated now by enormous seas. All once carpeted with the same gentle green fern. Then there is Lystrosaurus, a stocky, pig-sized creature with a beak like a turtle and 2 small tusks. It lived about 250 million years ago, just after one of the worst extinctions the planet has ever known. Its bones have been pulled from the rocks of South Africa, India, and Antarctica. the same animal in the same time slice, on 3 continents that today lie thousands of miles apart, separated by oceans no land creature could ever swim. For a long time, scientists tried to explain these matching fossils with land bridges. The idea was that long, narrow strips of land once stretched across the oceans, like sunken causeways, allowing animals and plants to walk from one continent to another. Then these bridges quietly slipped beneath the waves and disappeared. It was a tidy explanation, but it had a problem. The ocean floor showed no sign of any such bridges, no sunken ridges in the right places, no drowned highways of stone. Alfred Wegener saw the same fossils and reached a different conclusion. The bridges, he said, were not bridges at all. The continents themselves had once been joined. South America and Africa had been pressed together like puzzle pieces, with Mesosaurus paddling through lagoons that lay across the seam. Antarctica had once been warm enough for ferns. India had been nestled against Africa. The shape of the fossil record was not a story of vanished causeways. It was a story of a single landmass that had broken apart. For decades, that idea was treated as fringe. But the fossils kept piling up, always in patterns that ignored modern oceans and obeyed an older map. And eventually, the rocks themselves agreed. The same ancient mountain belts ran across continents that now sit far apart, matching at the broken edges. The same glacial scratches, carved by ice sheets 300 million years ago, ran in directions that only made sense if the southern continents had once been pressed together near the South Pole. What remains open, even now, is how complete the picture really is. New fossils still surface, and some of them shift the edges of the map. There are stretches of ancient time when we have only a handful of bones to work with, and whole regions of the deep past where the fossil record is nearly silent. Were there other creatures, other forests, other shared worlds we have not yet found? Almost certainly. The opposite shores still hold secrets. The stones on one coast still wait to be matched with stones on another, and somewhere in those quiet matches, more of the old supercontinent is still being slowly, patiently redrawn. Long before the continents took the shapes we know today, Pangaea wore a coat of green. Vast forests stretched across its low, swampy edges, and these forests were unlike anything alive now. They grew in a warmer, wetter world, fed by air thick with moisture and carbon dioxide. The trees were strange to modern eyes. They were not really trees in the way an oak or a pine is a tree. These ancient giants were closer to ferns and mosses, only grown to enormous size. Some rose more than 100 feet into the steamy air. Their trunks were not made of hard wood, but of soft, spongy tissue wrapped in a thick green skin. The bark was patterned with diamond shapes, or with neat rows of leaf scars, like the imprints of scales. When fossil hunters first found these patterns pressed into stone, some thought they had discovered the skin of a great reptile. The forests of that lost world grew in low, flooded basins. Slow rivers wandered through them, dropping silt and sand between the roots. Dragonflies the size of seagulls drifted between the trunks. Giant centipedes, longer than a grown person, moved across the damp floor. There were no flowers yet, no grasses, no songbirds. The air would have hummed with insects and rustled with the rattle of frond against frond. When these plants died, they fell into still, oxygen-poor water. There, they did not rot away in the normal manner. They piled up, layer upon layer, pressed down by their own slow weight. Year after year, century after century, the dead forests built up into thick mats of black, soggy peat. Over deep stretches of time, the peat sank deeper. Heat and pressure cooked it, squeezed the water out, and turned the soft plant matter into stone-like layers of coal. This is the quiet detail many people never quite hold in their mind. The coal we have burned for centuries is, in a sense, the body of a Pangaean forest. Each black seam locked in a basement, each lump pulled from a deep mine, was once a leaf, a stem, a root in a hot, humid swamp on a single great continent. The age that produced most of it is called the Carboniferous, which simply means coal-bearing. There is a tender mystery tucked inside this. The Carboniferous laid down more coal than almost any other span of Earth's history. Why this period and not others was so generous with coal is a question still being worked out. One idea is that the plants of that time had finally learned to make a tough substance called lignin, which gave their trunks rigid support. The fungi and bacteria that break down lignin today may not have existed yet, or may have been rare. So when the great trunks fell, nothing could fully digest them. They simply piled up, undisturbed, for tens of millions of years. Other researchers wonder if the answer lies more with the climate and the shape of Pangaea itself. The supercontinent had wide, low coastal plains sitting near the equator. These plains flooded easily and drained slowly. They became enormous nurseries for swamp forests. Perhaps the geography mattered as much as the chemistry. The question remains open, and the truth is likely a quiet braid of both. Slow down here for a moment and picture the patterns. Inside a piece of coal, under a microscope, you can sometimes see the fine ribs of a fossil leaf. You can see spores no bigger than dust grains, perfectly preserved. You can see the tubes that once carried water up through a green stem. The whole forest is still there, only flattened, dimmed, and turned to black glass. A geologist with a thin slice and a good lens can read it almost like a book. The fossils above the coal are just as gentle. Soft sandstones from those same swamps hold the prints of fern fronds in delicate detail. Each tiny vein, each curled tip is captured. Some slabs look as if a single leaf was pressed between 2 pages of stone yesterday afternoon. They are quiet keepsakes from a continent that no longer exists. So when you imagine Pangaea, do not picture only the bare brown shape on a map. Picture the green band along its equator. Picture the slow rivers, the towering club mosses, the soft fall of giant leaves into still water. Picture the patient layering of forests into peat and peat into coal, while the supercontinent itself sat quietly, not yet ready to break apart. The forests are gone. Their dark, compressed memory is still with us, hidden in the rock, waiting in the silence beneath our feet. Around 200 million years ago, something began to happen to the great supercontinent of Pangaea. The land that had stood as one began to split. Slowly, gently, almost too slowly for any single creature to notice, the surface of the Earth started to come apart. The mystery of how we came to understand this rupture is itself a long, patient story. It is a story told in stone, in maps, and in the quiet thinking of many people across many centuries. The first hints came from sailors and map makers. In the late 1500s, a Flemish map maker named Abraham Ortelius noticed something strange. The coastlines of the Americas seemed to match the coastlines of Europe and Africa. He wrote a short note suggesting that the lands had once been joined and were torn apart by floods and earthquakes. It was a quiet guess, almost a whisper, and the world was not yet ready to listen. His maps were beautiful, hand-painted on heavy paper, and his notes sat in their margins like a seed waiting for soil. For centuries, the idea drifted in and out of attention. A few thinkers picked it up, most set it aside. The notion that whole continents could move seemed impossible. The ground felt so still. The mountains felt so old. How could anything so vast slide sideways across the face of the planet? By the early 1800s, geologists began to find stranger clues. They found identical fossils of ancient ferns in rocks from South America and Africa. They found the same kinds of reptile bones on both sides of the southern oceans. They found bands of rock in Scotland that seemed to continue into Canada, as if a giant ribbon had been cut in two. Each clue was small. Each was easy to explain away. Land bridges, some said, long-lost paths now sunk beneath the waves. The mystery remained gentle, unsolved, waiting. Then came Alfred Wegener, working in the early 1900s. He gathered the scattered clues and pressed them together. He proposed that all the continents had once been a single mass, which he called Pangaea, and that this mass had broken apart and drifted to its present positions. He could not explain the force that moved them. That was the hole in his idea, and other scientists pushed their fingers into it. They dismissed his theory for decades. He died on an icy expedition in Greenland in 1930, never knowing he would one day be proven mostly right. The answer came slowly from the bottom of the sea. After the Second World War, ships began to map the ocean floor with sonar, sending pulses of sound into the dark water and listening for the echo. They discovered long ridges running down the middle of the oceans, like seams on a great fabric. They found deep trenches near the edges of continents, and they found something even stranger. The rocks of the seafloor carried a magnetic memory, frozen in place when the rock first cooled. In the 1950s and 60s, researchers towed sensitive instruments behind ships to read these magnetic patterns. They found that the seafloor near the ridges was young, and the seafloor far from the ridges was old. Stripes of normal and reversed magnetism ran parallel to the ridges, matching on either side like mirror images. The ocean floor was spreading. New crust was being born at the ridges and pushed outward in both directions. This was the engine Wegener had been missing. By the late 1960s, the picture finally came together. Continents were not plowing through the oceans on their own. They were riding on great slabs of the Earth's outer shell, slabs we now call tectonic plates. These plates moved together, pulled apart, and slid past one another. Pangaea had not simply broken. It had been torn open by the very floor of the seas growing wider beneath it. Geologists then turned back to the rocks of the continents themselves and read the timing of the rupture. They found that the first cracks of Pangaea opened around 200 million years ago, in what is now the area between North America and Northwest Africa. Long, narrow valleys formed first, filling with lakes and lava. Then the sea poured in. Slowly, the young Atlantic Ocean began to take shape. How long the full breakup took, and exactly why it began where it did, is still being studied. Some researchers think a great plume of hot rock rose from deep within the Earth and weakened the crust above. Others think the slow pull of sinking plates at the edges of Pangaea tore it open from the sides. The question remains open, drifting between theories like the continents themselves. The Atlantic Ocean feels eternal. Sailors have crossed it for centuries. Its waves seem older than memory. Yet in the long story of Earth, the Atlantic is young. It is, in geological terms, almost newborn. The water that rolls between the Americas and Africa fills a wound that began to open less than 200 million years ago. Before that, those distant shores were pressed together, dry rock against dry rock, with no sea between them at all. This is one of the strangest things about our planet. Oceans are not permanent. They open and close like slow, patient mouths. The Atlantic we know today did not always exist, and it will not exist forever. It began as a thin crack, a fracture deep in the heart of Pangaea, when the supercontinent began to pull itself apart. At first, that crack was nothing dramatic. It was a long valley, a rift, lined with volcanoes and hot lakes. Rain pooled in it. Lava bubbled up through it. For a long time, it stayed dry land. The first hints of the Atlantic look almost nothing like an ocean. Picture a long, narrow gash running from what is now the Gulf of Mexico up through the eastern edge of North America, past Greenland, and down toward what would become West Africa. In that gash, salt lakes formed. The climate was hot. The water evaporated again and again, leaving thick beds of salt buried deep beneath the modern seafloor. Those ancient salt layers are still there today, lying quietly under miles of mud and ocean water, a hidden record of the Atlantic's first breath. Then slowly, the sea came in. Some researchers believe the first marine waters spilled into the rift from the south, from a young ocean called the Tethys that had already begun to grow. Others suggest the connection came from the north. The exact path is still debated. What we know is that once the seawater arrived, the rift became a narrow seaway, something like the Red Sea today. Two coastlines faced each other across a thin band of salt water, separated by only a few dozen miles in places. A traveler could have stood on one shore and seen the cliffs of the other. That narrow sea did not stay narrow. The plates kept pulling apart slowly, at about the speed your fingernails grow. New seafloor formed in the middle, where hot rock welled up and cooled into fresh basalt. Year by year, mile by mile, the gap widened. The southern Atlantic opened later than the northern one, which is one reason the coastlines of Brazil and West Africa fit together so precisely. When you look at a map and notice how Africa seems to nestle into South America, you are seeing the memory of a tear that has not yet finished spreading. Here is the part that even experienced geologists find a little strange. The Atlantic is still growing. Every year it becomes about an inch wider. That sounds tiny, but stretched across millions of years, it is enormous. In the time it takes a human life to pass, the Atlantic widens by roughly the length of a tall person lying down. In the time since the first stone pyramids were built, it has grown by more than 100 feet. The ocean beneath the ships is not a finished thing. It is a work in progress. The middle of the Atlantic holds the seam where this growth happens. A long underwater mountain range runs nearly the entire length of the ocean, from north to south, called the Mid-Atlantic Ridge. Its peaks are taller than many mountains on land, but almost no one ever sees them. They are hidden under miles of dark water. Along the very center of that ridge runs a deep valley, and from that valley new seafloor is born. The youngest rock on Earth in many places lies along this hidden spine. What is still uncertain is exactly why Pangaea broke along the line it did. There are several theories. One idea is that a great plume of hot rock rose from deep in the mantle and weakened the crust just enough to crack it. Another is that the supercontinent had trapped heat beneath itself for so long that it eventually had to split, like a lid finally lifting from a pot. A third possibility is that pulling forces from sinking plates at distant edges did most of the work. Likely all three played some part. The full recipe remains an open question. So the ocean we think of as ancient is in truth quite young, and it is still being made quietly in the dark beneath the slow rolling of the waves. Not every continent stayed above the waves. Some sank, some broke into pieces too small to notice on a map. Some hide beneath shallow seas, their shapes only revealed by careful sonar and patient study. The story of Pangaea is also the story of these quiet, drowned places, the lost lands that connect one ocean to another, one fossil bed to another, one mystery to the next. The clearest example sits beneath the Southwest Pacific. It is called Zealandia. Most of it lies under water, with only New Zealand and a few smaller islands poking above the surface. The rest is a vast plateau of continental crust, drowned by perhaps a kilometer of seawater. Geologists now describe it as a true continent, thinner than the others, stretched and sunk, but made of the same kind of stone. It broke away from a larger landmass long ago, then thinned as it pulled apart, then settled below the waves. Why it sank so deeply, while other rifted lands stayed high, is still being studied. Zealandia is not alone. Beneath the Indian Ocean lies a long ridge of drowned rock known as Mauritius, a sliver of ancient crust that may have been left behind as India tore north toward Asia. Tiny grains of very old mineral, called zircon, have been found in young volcanic rock on the island of Mauritius. These grains are far older than the island itself. One theory is that they bubbled up from a buried fragment of continent hidden deep below. The fragment, if it exists, is a small lost piece of an older world. These drowned lands matter because they connect things. They help explain how plants and animals once moved between places that now seem far apart. A shallow bridge of sunken continent could have linked two coasts long after the deeper ocean opened. Seeds could drift across. Small creatures could island hop. Then, slowly, the bridge would sink and the two faunas would drift into isolation. The fossils on either side would look like cousins, separated by water that was once shallow enough to cross. This is where plate tectonics begins to sing with the rest of Earth systems. The slow motion of the plates does not just shape mountains and oceans, it shapes climate. It shapes the paths of currents. It shapes where life can spread and where it cannot. When a sunken continent rises slightly, it can split a current in two. When it sinks further, it can let cold water pour through a gap that was once closed. These small changes in ocean flow can shift rainfall thousands of miles away. A drowned plateau in one hemisphere can quietly steer storms in another. The sun joins this slow orchestra too. Sunlight warms the surface of the sea, and warm water flows toward the poles along paths carved by the shape of the continents. When Pangaea was whole, one enormous current likely spun around its single ocean, carrying heat in a way no modern sea can match. As Pangaea broke apart, new gaps opened, and the currents had to find new routes. Each new strait, each new sunken ridge, each new lost continent changed the global pattern of heat. The breakup of one land rewrote the weather of the whole planet. Volcanoes belong to this symphony as well. Where plates pull apart, magma rises and builds new seafloor. Where they collide, magma rises and builds tall cones along the edges. These volcanoes release gases, carbon dioxide, water vapor, sulfur, that drift into the atmosphere and shape the climate over millions of years. Long stretches of heavy volcanic activity can warm the planet. Long, quiet stretches can cool it. The position of the continents controls where these volcanoes line up, and that line determines how much gas reaches the air. Tectonics, in this slow way, helps set the thermostat of the world. Even the deep mantle plays its part. The drowned continents may sit above old slabs of cold ocean floor that sank long ago. Some researchers wonder whether these buried slabs tug downward on the crust above them, pulling one-stall lands beneath the sea. If so, the sinking of Zealandia, the thinning of Mauritius, and the quiet drowning of countless smaller fragments may all be linked to events that began hundreds of millions of years deeper in time. So a single drowned plateau holds many threads at once. It carries fossils that hint at lost bridges. It steers currents that move heat. It rests above mantle flows we cannot see. And it reminds us that the surface map of Earth, the one we learned as children, is only the part still high enough to be dry. The rest waits below, quiet and patient, holding its own version of the story. For all that we have learned about moving continents, one quiet puzzle still sits at the heart of the science. We know the plates move. We can measure them year by year as they slide a few centimeters across the globe. We can trace where they have been. We can map where they are going. And yet, when geologists ask the simplest question of all, what actually pushes them, the answers are still gentle and uncertain. For a long time, the leading idea was something called mantle convection. The mantle is the thick layer of hot rock that sits between the thin crust above and the molten core below. It is not liquid, but it flows very slowly, the way warm tar might creep across a stone in summer. Hot rock rises from deep down, cool rock sinks from the top, and in between, the rock moves in great, lazy loops. The thought was simple and beautiful. The plates float on top of these slow loops, dragged along like leaves on a slow river. But over time, the picture grew more complicated. Measurements showed that the deep loops in the mantle did not always match the direction the plates were drifting. In some places, the plates moved one way while the rock below seemed to flow another. The river and the leaf did not always agree. So researchers began to wonder if the mantle was only part of the story and not the whole engine. A second idea slowly gathered strength. It is called slab pull. When a plate sinks down into a trench, the the cold, heavy edge plunges into the warmer mantle below. That sinking edge is dense. It wants to fall. And as it falls, it tugs on the rest of the plate behind it, the way a heavy chain hanging off a table will slowly drag the rest of the chain over the edge. By this thinking, the plates are not so much pushed from below as pulled from their own sinking edges. Many geologists now believe slab pull may be the strongest single force at work. There is a third idea too, gentler and quieter than the others. It is called ridge push. At the great cracks in the ocean floor, where new crust is born, the fresh rock sits a little higher than the older crust around it. Gravity, patient as always, lets that raised ridge slowly slide downhill, pressing outward on the plates to either side. It is a soft force, but over millions of years, even soft forces can do enormous work. Most likely, all three ideas are partly right. The plates may move because of a quiet partnership between the sinking of cold slabs, the pushing of fresh ridges, and the slow turning of the hot mantle below. The puzzle is in the balance. How much does each one matter? Which one matters most? Whether that balance changes from one plate to another, or from one age of the Earth to another, these are questions geologists still sit with, turning them over like smooth stones in the hand. The Earth keeps moving while they wonder. The Atlantic widens by about the speed your fingernails grow. The Pacific shrinks at its edges as old seafloor sinks into deep trenches. India keeps pressing into Asia, lifting the Himalayas a few millimeters higher each year. East Africa is slowly splitting along a long, dry valley, where one day, perhaps, a new ocean will be born. None of this is fast. None of it is loud. But all of it is happening right now, beneath quiet villages and sleeping cities, beneath forests and frozen plains. What makes the mystery so soft, so suited to a slow night, is that the engine of all this motion is hidden from us. We cannot drill down to the deep mantle. We cannot watch the slabs fall. We piece the story together from echoes, from earthquake waves that pass through the planet, from the faint magnetism in old rocks, from satellites that measure the drift of continents to the millimeter. From these scattered clues, we try to picture a machine larger than anything human hands have ever built. A machine that has been running for billions of years and will keep running long after we are gone. The continents that once joined as Pangaea drifted apart because of forces we still do not fully understand. The continents around you tonight are still drifting for the same unclear reasons. Somewhere below the floor where you rest, hot rock is rising. Somewhere far out under the sea, a cold slab is sinking. The earth turns its slow gears, and the question of what truly drives them remains beautifully, patiently open. Somewhere in the middle of the Pacific Ocean, a line of islands rises from the deep blue water. The chain stretches in a long, gentle curve, with green peaks at one end and worn, sunken stones at the other. From above, the pattern looks almost drawn by a careful hand. These are the Hawaiian Islands, and they tell one of the strangest stories in all of plate tectonics. They are the work of a hot spot, a place where the earth seems to glow from deep below. A hot spot is a small region where heat rises up through the mantle in a narrow column. Imagine a slow candle burning far beneath the seafloor. Above it, the crust drifts along like a sheet of paper sliding across the flame. Wherever the paper touches the fire, it scorches and bubbles. The plate moves on, but the flame stays put. And so a new burn appears, and then another, and another, in a long line behind the moving plate. That, at least, is the picture many geologists have drawn for the Hawaiian chain. The youngest island, the Big Island, still glows with active lava. Its volcanoes pour out rivers of orange and red that hiss when they reach the sea. The light from those flows is one of the most beautiful sights on Earth. The molten rock starts out almost white at its hottest, then cools through yellow, into deep orange, and finally into a dim red crust that hardens into black stone. Travel northwest along the chain, and the islands grow older, greener, and more worn. Maui, Molokai, Oahu, Kauai. Beyond them, the islands shrink into tiny atolls, then into bare reefs, then into nothing more than flat seamounts hidden under the waves. The further you go, the older the rock. The light that once poured from those vents has long since faded. What remains is only the cooled memory of an ancient glow. If the simple picture is true, then the Pacific Plate has been sliding northwest over a steady flame for tens of millions of years. The chain even bends, partway along its length, in a sharp angle called the Hawaiian Emperor Bend. Many researchers think this bend marks a moment when the plate changed direction. Others wonder if the hot spot itself moved. The question is not fully settled. That is where the mystery begins to deepen. For a long time, hot spots were imagined as fixed points, anchored to something deep and unmoving in the lower mantle. They were the still candles beneath the drifting paper, but newer studies have suggested that some hot spots may wander slowly on their own. A few may even rise from shallow sources, not from the very bottom of the mantle. The old, tidy picture has grown blurrier. There is also the question of why hot spots exist at all. Most volcanoes appear at the edges of plates, where crust pulls apart or dives down. Hot spots break that rule. They burn in the middle of plates, far from any boundary. One leading idea is that thin plumes of hot rock rise from near the core, all the way up through the mantle, like slow lava lamps inside the Earth. Other researchers are not convinced. They wonder if some hot spots are caused by cracks in the plate, or by old, trapped pockets of heat, or by something else entirely. A few hot spots glow with such force that they have shaped the planet in dramatic ways. The Yellowstone region in North America may sit above one. Iceland, perched on a spreading ridge, sits above another. The volcanic island of Reunion in the Indian Ocean may be the small, modern descendant of a much larger ancient hot spot that once poured out enormous floods of lava in what is now India. These vast lava floods are called large igneous provinces, layers upon layers of dark basalt that cooled in place. Some geologists think the largest of them were born from the heads of giant plumes rising for the first time. Others think the story is more complicated. The light those eruptions threw across the ancient sky must have been astonishing, yet no one was there to see it. What we have today are the quiet remains, black rock, worn islands. Sunken seamounts trailing into the deep, a faint chain of clues across the ocean floor, marking the path of a plate over a flame that may or may not have stayed still. The light is real. The pattern is real. The cause is still being debated. For tonight, picture the slow glow at the bottom of the sea. The plate drifts, the candle burns, and the question of where exactly that candle is anchored remains gently, beautifully open. Stone has a kind of memory. It does not speak in words, of course, but when the ground moves, when two great slabs of rock shift past each other deep below, the earth makes a sound, a low rumble, a deep hum that travels through the planet like a bell that has been gently struck. Geologists have learned to listen for these sounds, and in listening, they have learned to read the slow story of the plates. Most earthquakes are quiet things, at least from a human point of view. The ground trembles for a few seconds, then settles. But underneath that brief shaking, the rock itself is releasing energy that has been stored for hundreds, sometimes thousands of years. The plates push against each other. They lock, they strain, and then in a single moment they slip. The release sends waves through the body of the earth. Some of those waves travel along the surface. Others dive deep, passing through the mantle, bending around the core, emerging on the far side of the planet hours later. Each kind of wave has its own voice. The first to arrive are called P waves, short for primary. They push and pull the rock in the same direction they travel, like a long spring being squeezed and released. They are fast, and they can pass through almost anything, even liquid. Behind them come the S waves, the secondary waves, slower and rolling, shaking the rock sideways. S waves cannot pass through liquid, and that single fact told early geologists something remarkable. By tracking which waves arrived where, they realized the outer core of the Earth must be molten. The planet was reading itself aloud, and a small group of patient listeners learned how to hear it. When you slow these waves down or speed them up, they become something you can almost hear with your ears. A distant earthquake played through a speaker sounds a little like deep thunder or the long groan of a settling house. Recordings of seismic waves from quiet days when no quakes are happening reveal a constant, soft hum. The earth is always humming. The cause is not fully settled. One idea is that ocean waves, pressing rhythmically against the seafloor, set the whole planet ringing at very low frequencies. Another suggests that wind and weather contribute. The hum is faint, far below human hearing, but it is always there. There is something gentle about the thought of a humming planet. A world that vibrates softly beneath your feet, even on the calmest morning. The stones beneath the soil are not silent. They are simply speaking too slowly and too low for us to notice without help. The memory in stone runs deeper still. Where two plates have ground past each other for millions of years, the rock keeps a record of every slip. Scratches called slickensides shine on the broken faces of old faults. They run in the direction the rock once moved. Bands of crushed and powdered stone, called fault gouge, mark where pressure turned solid rock into something almost like flour. By studying these scars, geologists can read the rhythm of past quakes, sometimes stretching back thousands of years before any written history. Along the edges of certain plates, scientists have found something stranger. Slow earthquakes, tremors that last for days or even weeks, releasing energy so gradually that nothing on the surface feels them. They were only discovered in the last few decades, once instruments became sensitive enough to notice. What causes them is still being worked out. One theory points to fluids trapped between layers of rock, lubricating the slip. Another suggests that the temperature and pressure at certain depths allow rock to behave almost like soft clay. The questions remain open. The plates, it seems, have more than one way of moving. There are also mystery sounds in the ocean. Hydrophones lowered into the deep have picked up long, low calls that no one can fully explain. Some seem to come from underwater landslides. Some may come from ice scraping across the seafloor at the poles. Others have no agreed source at all. They are gathered, catalogued, and given gentle names, and they wait for someone to understand them. All of it together makes the Earth feel less like a silent stone and more like a slow, breathing instrument. The plates groan, the faults creak. The deep hum continues beneath every footstep, beneath every quiet night. The planet remembers each slip, each strain, each release, and writes it into the rock. And somewhere in that long, low music, there are still notes we have not learned to read. There are still sounds we have not yet placed. The stones are speaking. We are only beginning to listen. There is a kind of quiet music written into the floor of the ocean. You cannot hear it and you cannot see it with your eyes, but it is there, lying in long ribbons of stone, stretching across the dark seabed in patterns that look almost too neat to be real. These patterns are called magnetic stripes, and they are one of the most beautiful clues the Earth has ever given us. To understand the stripes, we have to start with a simple idea. The Earth itself is a giant magnet. Deep in its outer core, hot liquid iron swirls and flows, and that motion creates a magnetic field that wraps around the whole planet. This field has two ends, a north and a south, and most of the time it points the way our compasses point today. But the field is not fixed forever. Every so often, over long stretches of time, it flips. North becomes south, south becomes north, and then, eventually, it flips back. We do not know exactly why the field reverses. We do not know exactly when the next one will come. But we do know it has happened many, many times in the past, because the rocks remember. Here is where the math becomes lovely. When fresh lava rises along the mid-ocean ridges and cools into new seafloor, tiny mineral grains inside the rock line up with the magnetic field of that moment. They lock in like little frozen compasses. As the seafloor spreads outward, year after year, new lava rises in the middle, and the older rock is carried slowly to either side. Each time the field flips, the new rock records the new direction. So the seafloor grows outward in matching pairs, like two mirrors moving apart. When ships first dragged magnetic sensors across the ocean in the middle of the 20th century, they found something astonishing. The seafloor was not magnetized in one smooth sheet. It was striped. Long bands of normal magnetism, then long bands of reversed magnetism, running parallel to the ridges and matching almost perfectly on either side. It was as if someone had laid down a barcode, and then a mirror image of that same barcode on the other side of a long crack in the earth. This was the moment the theory of plate tectonics truly came to life. The stripes proved that the seafloor was moving. They proved it was being made at the ridges and carried away. And they did it with numbers so clean and so symmetrical that they could not be explained any other way. The math hidden in the stripes is gentle but precise. By counting the bands and knowing how often the magnetic field has flipped, geologists can measure how fast the seafloor is spreading. In some places, the answer is about 2 centimeters a year, roughly the speed your fingernails grow. In other places, it is closer to 15 centimeters a year. These numbers seem small, but across millions of years, they open whole oceans. There is something deeply soothing about this. Every wide sea on Earth was once a thin line of fire. Every coast that faces another coast across a vast blue distance was once joined. The stripes on the seafloor are the slow ledger of that parting, written in iron, kept in the dark, waiting to be read. And yet, even here, in this clean and elegant pattern, mysteries remain. The reason the magnetic field flips is still not fully understood. The flips do not come on a regular schedule. Sometimes the field stays steady for tens of millions of years. Sometimes it flips several times in a single million. One idea is that small changes in the flow of the molten core build up until the field collapses and rebuilds in the opposite direction. Another idea looks at how the boundary between the core and the mantle might shape the flow above it. The question remains open. We also do not know what a reversal feels like from the surface. The last full flip happened around 780,000 years ago, long before written history. The field weakens during such transitions, but life carried on through every one of them. The fossils tell us so. Still, the details are blurry, and the next reversal, whenever it comes, will be a slow and quiet event spread across many human lifetimes. For now, the stripes lie in the dark, waiting. Long bands of stone, magnetized one way and then the other, drifting outward at the speed of a growing fingernail. A barcode of deep time, a song in iron, sung by a planet that has been keeping its own careful count for billions of years, in a language we are only beginning to read. Pangaea was not the first supercontinent. It was simply the most recent one. Long before Pangaea pulled itself together, other supercontinents rose and broke apart in the slow turning of the Earth. There was Rodinia, which formed about 1 billion years ago and shattered hundreds of millions of years later. Before Rodinia, some geologists believe, there was a still older gathering of land called Columbia, and perhaps one before that called Kenorland. The pattern seems to repeat. Continents drift, collide, fuse into one great mass, sit together for a while, and then slowly tear apart again. The full cycle takes around 400 to 600 million years. Geologists call this the supercontinent cycle, and it is one of the deepest rhythms on the planet. The Earth seems to breathe in and out across spans of time that no human mind can really hold. Why this rhythm exists at all is still an open question. One idea is that when continents gather into a single mass, they trap heat in the mantle below. The hot rock has nowhere to release its warmth. Over time, the pressure builds, and the supercontinent splits along the weakest seams. Another idea is that the cold slabs of seafloor sinking into the mantle pull the continents into new arrangements, like cloth dragged across a table by its hanging edge. Both ideas may be partly true. The full picture is still being pieced together. What is remarkable when you sit with it is how delicate this whole arrangement seems to be. The Earth is the only world we know of where plate tectonics still works. Venus is nearly the same size and made of similar stuff, but its surface is locked in place, one solid shell with no moving plates. Mars once had volcanoes far larger than any on Earth. but its outer layer cooled and stiffened long ago. Something about our planet has kept the engine running for billions of years, and no one is entirely sure what that something is. Water may be part of the answer. The oceans soak down into the seafloor, and that water lowers the melting point of rock far below. Some researchers wonder whether plate tectonics needs liquid water the way a wheel needs grease. Without it, the plates might seize up, and the slow cycle of supercontinents would come to a quiet halt. If that is true, then the oceans above and the moving plates below are linked in ways we are only beginning to understand. The temperature inside the Earth matters too. If the planet had cooled faster, the mantle would already be too stiff to flow. If it had cooled more slowly, the crust might never have hardened enough to break into plates at all. Earth seems to sit in a narrow band where the rock below is hot enough to creep, but cool enough to crack. That balance has held for billions of years, but no one knows exactly how long it will last. Even the thin shell of air around us plays a quiet role. The atmosphere keeps temperatures steady enough for oceans to exist. The oceans feed water into the plates. The plates carry carbon back into the mantle through subduction, and volcanoes release it again, keeping the air in a long, slow chemical balance. Remove any single piece of this system, and the rest may begin to drift towards some other state. We do not know how forgiving the system really is. The distance from the sun is part of the picture too. A little closer, and the oceans might boil away. A little farther, and they might freeze into permanent ice. Our planet sits in a narrow ring where liquid water can rest on the surface, and where the heat from the sun, the heat from below, and the gases in the air all settle into a kind of long, slow agreement. When you think about it this way, the supercontinent cycle starts to feel less like a fact and more like a small miracle stretched across deep time. The continents drift because the mantle flows. The mantle flows because the planet is still warm inside. The planet stays warm because of slow radioactive decay in its deep rocks, set in motion when the Earth itself first formed. Every step depends on the last. Whether this rhythm will continue for another billion years or slowly fade as the planet cools is one of the quieter mysteries in geology. The next supercontinent may form, or the engine may begin to wind down. The system has held so far. How long the balance will last is a question still waiting in the stone beneath our feet. The plates are still moving tonight. They have not stopped. The same slow forces that pulled Pangaea apart are still at work beneath your feet, still rearranging the surface of the world. And so a quiet question follows naturally from everything we have wondered about so far. If supercontinents come and go in long, slow cycles, then another one is on its way. We just do not know what shape it will take. The continents we see today are not finished things. Africa is still pressing into Europe, slowly closing what is left of an ancient sea. The Atlantic Ocean is still widening, pushing the Americas a little farther from Europe and Africa each year. Australia is drifting north toward Asia at a steady, patient pace. India keeps grinding into the underbelly of Asia, still lifting the Himalayas higher. None of these motions are settled. They are scenes in the middle of a much longer story. Geologists have looked at these motions and tried to imagine what the world might look like in 200 million years, or 300 million, or even further. They have given the possible futures names, and each name belongs to a different theory about which way the plates will turn. One idea is called Pangaea Proxima. In this picture, the Atlantic Ocean stops widening at some point in the deep future. New zones form where the seafloor begins to sink back down into the mantle. The Americas slow, then reverse, then drift back east. They collide once more with Europe and Africa, and the old wound of Pangaea closes again. Australia joins from below, and a new supercontinent gathers near the equator, wrapped around a warm inner sea. A different idea is called Nova Pangaea. In this version, the Atlantic keeps widening for a very long time, and it is the Pacific that closes instead. The Americas drift west, sliding toward Asia across the slowly shrinking Pacific floor. Eventually they meet. Australia is already on its way north, and Antarctica may follow. The new supercontinent gathers on the far side of the world from where Pangaea once sat, centered roughly where the Pacific is today. There is a third idea, called Amasia. In this picture, the plates drift mostly northward, drawn toward the cold cap of the Arctic. North America and Asia meet near the pole, with other continents trailing behind. The new supercontinent forms in the high north, while the southern half of the world becomes one vast open ocean. A fourth idea, sometimes called Orica, gathers most of the land near the equator from a different direction entirely. 4 pictures, 4 futures, and we do not know which one, if any, is right. The reason we do not know is that the forces underneath are still not fully mapped. The hot, slow churning of the mantle is the engine that pushes the plates, but the exact pattern of that churning is hidden from view. We can take soft images of it using earthquake waves, the way a doctor uses sound to see inside the body. The images are blurry. They show hot plumes rising in some places and cold slabs sinking in others, but the fine details are still being worked out. Small changes in those deep currents could send a continent one way instead of another. There is also the question of what happens when an ocean basin grows old. Some scientists believe that very old seafloor becomes heavy enough to begin sinking on its own, opening new trenches and pulling its continent back. If that is true, the Atlantic may be approaching that age. If it is not true, the Atlantic may keep widening for hundreds of millions of years more. The answer changes which future we end up in. None of these models are predictions in the way a weather forecast is a prediction. They are more like careful guesses, drawn from what we know about how plates have moved in the past. They invite us to imagine, not to be certain, and the imagining itself is part of the science. Each model gives geologists something to test, something to compare against the slow drift we can measure today with satellites. What is certain is only this: the continents will keep moving. Some ocean will close, some new ocean will open. The land you live on will one day touch land it has not touched in hundreds of millions of years. The map of the world will be redrawn, and then redrawn again, long after every human map has been forgotten. Which way the next supercontinent will gather, and what its inner seas will look like, and where its great mountain ranges will rise, these are open questions still. The Earth has not made up its mind, or perhaps it has, and we simply cannot read the answer yet. When you stand at the foot of an old mountain, you see only the part above the ground. The peaks rise into the clouds, the slopes fall away into valleys, and snow may rest on the shoulders of the stone. Yet most of the mountain is hidden. Deep below the surface, the rock extends downward like the root of a great tooth. These hidden roots can reach tens of miles into the earth, far deeper than the mountain is tall. The roots form because mountains are heavy. When two plates collide and push the crust upward, the thickened rock also sinks downward into the softer layer beneath. It is a little like a wooden block floating in water. The taller the block stands above the surface, the deeper it sits below. Geologists call this balance isostasy, the slow way the Earth's crust floats on the warm, flowing rock of the mantle. These deep roots tell a long story. Long after the peaks have worn away, the roots remain. Wind and rain take millions of years to grind a mountain down. Rivers carry the dust to the sea. Glaciers scrape away the higher slopes, but the root below keeps the memory of the mountain alive, hidden under flat plains where nothing seems to have happened. In parts of Canada, Scandinavia, and Western Australia, the ground today looks quiet and low. Yet beneath the soil, geologists have found the worn-down roots of mountain ranges that once stood as tall as the Himalayas. These ancient ranges rose during the building of older supercontinents, long before Pangaea formed. Their peaks vanished hundreds of millions of years ago. Only the cold, dense roots remain, deep in the crust, like fossils of vanished giants. What will happen to today's mountains in the far future is one of the gentler open questions in geology. The Alps, the Andes, the Rockies, the Himalayas, all of them are still rising in places, pushed up by plates that keep pressing together. But erosion is always working too. In a few 100 million years, many of the peaks we know now may be gone. Their roots, however, may still be there, buried under younger soil and forest. Some researchers wonder whether the deep roots of mountains play a role in shaping the plates above them. One idea is that thick roots act like keels under a ship, helping to steady the older parts of continents as they drift. These steady old cores are called cratons, the ancient hearts of the land masses. They have survived for billions of years, even as oceans opened and closed around them. Why some pieces of crust last so long, while others are pulled down and recycled, is still not fully understood. Looking forward, the picture becomes even more uncertain. In a million years, the continents will have shifted only a small distance, perhaps a few dozen miles. The shape of the world will feel familiar. In 10 million years, the Red Sea may have widened into a young ocean. East Africa may have begun to split away from the rest of the continent. In 100 million years, the Atlantic may stop growing and begin to close. New trenches may form along its edges, slowly pulling the seafloor back down. In a billion years, the surface of the Earth will look like a stranger's face. New mountains will rise where none stand now. Old ranges will be ground flat. New oceans will open and close. New supercontinents may form and break apart, perhaps more than once. The deep roots of today's peaks may still be there, hidden far below, while the surface above takes on shapes no human will ever see. Far beyond that, the sun itself will change. In several billion years, it will swell and brighten, and the conditions on the surface of the Earth will shift in ways that are hard to picture. But the slow churn of the mantle, the drifting of plates, the quiet rising and wearing down of mountains, These processes will likely continue for a long time before they finally slow and stop. The Earth's inner heat fades very slowly. Plate tectonics may keep going for another billion or 2 billion years before the engine cools enough to still. What is certain is that the planet is always becoming something new. Nothing about the map is permanent. Even the bones of the oldest mountains, deep in the crust, are part of a slow story still being written. The peaks you know today are simply the latest verse. The roots beneath them carry the older verses, and the verses still to come are gathering quietly in the warm rock far below your feet. After so many hours of slow wondering, it helps to step back, to pull away from the maps and the fossils and the slow grinding of stone, and to see this whole story from a great distance. Plate tectonics is not just a feature of our planet. It is part of a much older story, one that began long before Earth itself. The atoms in the rocks beneath your feet were not born here. The iron in the core, the silicon in the crust, the calcium in the cliffs along the sea, these elements were forged inside ancient stars. When those stars ended their lives, they scattered their atoms across the cold dark of space. Some of those atoms drifted for billions of years before gathering into the cloud of dust that became our solar system. The mountains that rise and fall on Earth are made of starlight, slowed down into stone. The same is true of you. The calcium in your bones, the iron in your blood, the oxygen in every breath, all of it came from the same ancient furnaces. In a quiet way, you are kin to the continents. You and Pangaea share a deep common ancestor written in atoms. This is the wider view that geologists sometimes sit with at the end of a long day. The drifting plates, the rising ranges, the opening oceans, these are not separate events. They are part of a single slow process by which a planet sorts itself out. Heavier things sink, lighter things rise. Heat moves from the inside toward the surface. The whole Earth is breathing, very slowly, across spans of time we can barely imagine. And yet, for all that we have learned, the open questions remain. Geologists still ask why plate tectonics began at all. They ask why our planet is the only one we know of with continents that drift across its face. Venus is nearly the same size as Earth, made of similar stuff, and yet its surface does not seem to move in the same way. Mars may have had some early tectonic activity, but it stopped long ago. Why did our world keep going? Why did the engine here stay warm and restless while others cooled into stillness? One idea is that water made the difference. Liquid water on the surface may have softened the rocks enough to let them slide. Another idea is that early impacts from large objects cracked the young crust into pieces that could move. A third possibility is that life itself, by changing the chemistry of the oceans and air, helped keep the cycle turning. The honest answer is that we do not yet know. Several theories sit beside each other, none of them complete. Geologists also still ask when plate tectonics really began. Some evidence suggests it started more than 3 billion years ago. Other evidence points to a much later beginning, perhaps only 1 billion years ago. The rocks from that distant time are rare and hard to read. The question remains open. There is also the question of how long this will continue. The Earth is slowly losing its inner heat. One day, far in the future, the engine will grow quiet. the plates will stop moving. The mountains will wear down with no new ones to replace them. The continents will settle into one final shape, but that day is so far away that it has no real meaning for us tonight. For now, the engine still runs, the plates still drift, the story is still being written. And here is the part that may be the most quietly astonishing. We are the first creatures on this planet, as far as we know, who have ever understood any of this. For 4.5 billion years, the continents moved and no one watched. The supercontinents gathered and broke apart in silence. Then, in the last small sliver of time, a species appeared that could look at the rocks and read their slow language. That species is us. You are part of that. By lying here, listening, wondering about the drift of continents, you are taking part in something the Earth has never had before, a witness. A mind that notices, a heart that finds the slowness beautiful instead of frightening. The plates beneath you are moving as you breathe. The atoms in your body once burned inside a star. The rocks beneath the ocean are remembering magnetic fields older than any human story. And somewhere in the deep quiet, the next supercontinent is already beginning to gather. We may never see it, but it is coming slowly, patiently, in its own time. And so we come to the quiet end of our long, slow walk across a moving world. The facts have been gathered. The wonders have been shared. The questions, most of them, remain open, the way they should be when the mystery is honest and the answers are still forming somewhere deep in the rock. Let yourself rest now. Let the body settle into the bed beneath you. Let the breath grow soft and even. The Earth is moving, just as it always does, in the quiet way it has moved for billions of years. The plates beneath you are drifting at the pace of a fingernail growing. The continents are sliding, gentle as a sleeping animal turning in its dreams. Picture the planet from a great quiet distance, a blue and white sphere spinning slowly in the dark. The oceans hold the soft silver of moonlight. The clouds curl in long pale ribbons across the sea. The land glows faintly where cities sleep, and the dark forests breathe out cool air into the night. Somewhere a glacier creaks. Somewhere a wave folds itself onto a quiet shore. Somewhere a mountain is rising by the width of a hair. You are held by all of it, by the crust beneath your home, which floats on a slow river of warm stone, by the deep mantle, which carries heat from the core in patient, looping currents, by the iron heart of the planet, which spins and gives us our magnetic field, the soft, invisible shield that has guarded life for ages beyond counting. There is comfort in knowing how slow it all is. The Atlantic widens by about an inch a year. The Pacific narrows by something close to the same. The Himalayas climb a little higher with every season, and the old worn hills of ancient ranges sink a little lower. Nothing rushes. The earth has time. So tonight, do you think of the long story we walked through together? A single great continent called Pangaea, surrounded by one vast sea. The slow tearing apart of that land. The birth of new oceans where there had been none. The drifting of pieces across the face of the world, carrying their fossils and their forests with them. The hot spots that stayed still while the plates slid above them, leaving long chains of islands like footprints in the sea. The deep trenches that swallowed old crust and returned it, melted and remade to the surface. The magnetic stripes written in the basalt of the ocean floor. a quiet record of every flip and turn of the planet's iron heart. And the questions, so many open questions. What truly drives the plates? Whether the deepest plumes really rise from the core, or only from somewhere shallower. How many lost continents lie hidden under the seas? What the next supercontinent will look like, and whether we have given it the right name. Whether the cycle of gathering and breaking apart will continue forever, or whether one day the engine will grow cool and the surface will fall still. You do not have to answer any of it. The geologists are working on it patiently with their cores and their seismometers and their long, careful papers. They will keep working long after this night is over. The mountains will keep rising. The oceans will keep widening. The plates will keep drifting in their slow, dreaming way. For now, all you have to do is breathe. In and out, slow and easy. The bed beneath you is steady. The room around you is quiet. The planet beneath the room is moving, gentle as a long exhale, carrying you with it through the dark. We may learn more in our lifetime. We may not. New instruments will go down into the deep. New maps will be drawn. Some old ideas will fall away, and some new ideas will rise to take their place. The story of the moving Earth is not finished. It has only paused for the night, the way good stories do, waiting for us to come back when we are rested. Let the wondering carry you down into sleep. A quiet planet spinning in a quiet dark, an ocean resting under a calm moon. A continent drifting, slow as a thought, toward a shore it will not reach for 100 million years. You are small, and the world is vast, and the vastness is gentle tonight. Rest now. The mountains will keep growing without you. The seafloor will keep spreading without you. You have done enough for one day on a moving Earth. Subscribe for a brand new Earth topic every night. One tap and something wonderful is waiting for you tomorrow. Sweet dreams.